Hello dear student, welcome to the last lecture in tensor analysis. In this video, we will be talking about the Riemann-Christoffel tensor. In detail, we will be looking into the very notion of curvature. We will try to define curvature using parallel transport. Then we will define the Riemann curvature tensor, the Ricci curvature, and also the Einstein curvature tensor, which will lead to develop the Einstein's field equation. So let us define the term curvature. We were using this term many times in our previous lecture videos, but we haven't defined it yet. So let us give a try to define the very notion of curvature. Here I am trying to define curvature using the parallel transport theorem, which we have understood in our previous lecture videos. Consider this small red triangle which is plotted on a two-dimensional space, that is the space of your screen. Now I consider a vector here. And let me try to parallel transport this vector along the contour of this two-dimensional triangle. When I parallel transport this vector, I will get back the same vector at its initial point. That is, when I parallel transport this vector from A to B to C and back to A, what I will get is the same vector with same components in the same direction. That is, the parallel transport yield me the same vector. Now consider a two-dimensional space and a three-dimensional manifold. Here I parallel transport along a triangle which is plotted along its dimensions. See, in a two-dimensional triangle, which is a Euclidean triangle, you have learned that the sum of interior angles is 180 degree. But here in the case of a curved space, you can see that this triangle, when I consider a triangle ABC here, the side AB makes an angle 90 degree. Again, this makes an angle 90 degree and here it makes an angle 90 degree. From this you can see that the sum of interior angles is not 180 degree but 270 degrees. Now consider another vector here and I parallel transport along a triangle which is drawn on a curved space. If I parallel transport this along the straightest path which is possible, remember, when you are a one-dimensional being living on this surface, the straightest path possible for you is a curved path. So when you transport yourself along the straightest path possible, you will hit the equator with an angle 90 degree. And along, again you parallel transport your vector from B to C and you will hit again at C at an angle 90 degree. And again parallel transport it to A and see that our final vector and initial vector are separated by an angle 90 degree, which was not the case when you parallel transported it along a two-dimensional triangle. So see that this difference in the initial vector and the final vector while parallel transporting was just an outcome of how curved the space is. You can actually do this experiment at home when you catch a ball, get a ball and try drawing a triangle and try making parallel transporting different vectors along its space. Not just in this direction, in any direction. Try parallel transporting different vectors and see that the difference between the vectors is actually 90 degrees. Now you can see that I have defined the notion of curvature using parallel transport. That is, the curvature is an outcome, or I can say that when a vector is parallel transported, if it doesn't give you the same vector and it deviates from its initial vector, then the space must be curved. And how much it is curved? It depends on how much the initial and the final vector varies. If you try this parallel transport on a torus, then you can see that the difference between the initial and the final vectors vary significantly. So I define curvature as how two initially parallel trajectories cease to be parallel at some point. To define or to quantify the very notion of curvature, I can analyze the behavior of a vector which is parallel transported on a non-infinitesimal region in a curved manifold. But remember, it is okay to be in a local Lorentz frame, but we can transport it in a non-infinitesimal region, a significant region in a curved manifold. And you can see that the vector in which the initial and the final vectors are, angle to which the initial and the final vectors are rotated is equal to sum of internal angles of a triangle which is drawn on that surface minus 180 degree. You know that 180 degree is the sum of internal angles on a Euclidean space. So this angle actually tells us how much my manifold has deviated from the normal Euclidean space, and this deviation is definitely its curvature. Now let me try to show you the notion of curvature using parallel transporting any vector along a space along a closed contour. Here I have chosen two coordinates, x sigma and x lambda, and also two other coordinates which is slightly different from the initial coordinates. And I define a region A, B, C, D, that is the closed curvature. Now when I move from A to B, actually I am moving in the increasing direction of x sigma. Sigma and lambda are just another parameters which we have defined as affine parameter, and x lambda and x sigma are just coordinates, and this line x sigma plus dou x sigma is a curve which is just adjacent, and x lambda plus dou x lambda is another curve which is just adjacent to x lambda. Now let me parallel transport any vector from A to B to C to D and back to A, and calculate the difference between these vectors, the initial vector and the parallel vector, and try to quantify the nature of curvature of the field which I am trying to deal with. Now when I move from A to B, actually I am moving in a direction of increasing sigma, or I can say that my motion is a scalar multiple of anything that is in the direction of the unit vector along E sigma. Similarly, when I am moving from B to C, it is in the increasing direction of a lambda, that is along the unit vector of lambda. Now I parallel transport a vector V alpha from A to B. When I parallel transport it from A to B, I am moving along the unit vector E sigma. So since it is parallel transport, the covariant derivative of the vector V alpha with respect to in the direction of E sigma have to be equal to 0. We know that we know the structure of covariant derivative. It has a partial derivative and also the Christoffel symbol which is equal to 0. I can just rearrange it and write, and that is I can just bring my Christoffel symbol to the other hand side, and write that the partial derivative of V alpha with respect to X sigma have to be equal to negative of, because I brought it in the other side, the Christoffel symbol into V mu. Now I can find the value of V alpha just by integrating this equation over here. I can integrate with respect to X sigma. When I integrate it, I will get an integral which is along the path 1. Let me talk around the path 1. Take it as along path 2, 3 and 4. Plus a constant. When I give the initial condition that the V alpha at time is equal to 0 or the sigma is equal to 0 was V initial. Therefore, I can get it as V alpha at B. Now, this is the V alpha at B is equal to V alpha, which was the initial V alpha, that is V alpha at A, minus this integral. Now, if I try parallel transporting all along all the vectors which I have, that is, now I have parallel transported a vector from A to B. Now I have V alpha at B. Now again I parallel transport it along the line 2, and when I parallel transport it along the line 2, then I have V alpha at C and V alpha at C. Similarly, using the same denotations, I can write V alpha at C is V alpha at B, that is the initial, minus integral over 2 of the function. Again, V alpha at D, that is when I parallel transport the same vector to D, what I will get. This is V alpha at D, and you can see that we here have a plus sign. This is because when I parallel transport it along the range C, actually I am coming in the negative X E alpha direction. We know that this is a positive E alpha direction when I move from X sigma to X sigma plus dx sigma. Here I am transporting it in the negative direction, that is in the negative E sigma direction. That's why I have a positive sign over here. Similarly, when I transport it back to A, that is V alpha final. V alpha final is nothing but V alpha of A is Vd plus integral over the fourth path and this function over here. Now see that I can back substitute all these, that is I can substitute for V alpha of D from this equation, and again in this equation you will have V alpha of C, then back substitute from here and back substitute from here, and you will end up with V alpha final, V alpha initial and four integrals over here. And I can just write all these 4 integrals over here as delta V alpha. That is, this 4 integrals over here actually tells me how much it has deviated from its initial and the final positions. So V alpha final is equal to V alpha initial minus this deviation over here, which is written using 4 integrals. So the V delta V alpha is again V4 integral over the fourth direction, integral over second direction, integral over third direction minus integral over first direction. You can see that the function in here in integral over 4 and integral over 2 are the same, and the function over here in integral over 3 and integral over 1 are the same because they are just parallel paths. You can see that the second and the fourth path are parallel, while first and the third path are parallel. They are parallel but an offset path. So the function which is inside the integral of the fourth and the second as well as first and the third functions are the same. Now we have that we know that the functions here and here are the same, since they are parallel but offset path, and they differ only by delta sigma, which is a very small deviation, and here also they deviate only by delta lambda, which is a very small deviation. We can use the binomial theorem and use the second order Taylor corrections here. If you do not know what is the second order Taylor correction, I recommend you to go back to the Liouville's theorem in Hamiltonian dynamics, where we have done this using second order Taylor corrections. So I will bring in some second order Taylor correction, and actually I can club these two integrals and these two integrals and write these four integrals as just two integrals using the Taylor correction, where this deviation or the integral ranges from x sigma to dx sigma, and another integral ranging from x lambda to x lambda plus dx lambda. And you can see here I have a derivative and two functions over here. So when I take a derivative of these, I will again end up with 4 terms, but I can get rid of this sigma using the Taylor corrections. And now I take the derivative. The first portion will be the partial derivative of the Christoffel symbol into mu nu plus Christoffel symbol into partial derivative of mu nu. Here also partial derivative of Christoffel symbol into mu nu plus mu nu into partial derivative, Christoffel symbol into partial derivative of mu nu. You already know that is using the parallel transport, that is covariant derivative form. You know that this delta sigma actually stands for the symbol partial derivative with respect to this. So this is actually from our covariant derivative form. We have seen that the covariant derivative is equal to 0 because we are dealing with parallel transport. So from that I can rewrite this partial derivative of mu nu as Christoffel symbol and partial derivative of mu nu with respect to sigma using another Christoffel symbol. Again, substituting this, I will get 4 terms and I can rearrange it in this form. Here, see, we have square of Christoffel symbols here. You might have already heard that the theory of relativity is non-linear theory of gravity. Yes, this non-linearity comes from here. See, here we have square terms, and the non-linearity in the theory of relativity actually comes out from here. Now, I can just relabel u and mu from the symmetry of Christoffel symbols, and just rewrite this entire term as delta v alpha can be rewritten in this form, that is delta sigma of lambda delta x lambda v nu, with these all terms comprised into one quantity, that is r mu lambda sigma. See, we have now just used the parallel transport to quantify curvature. This is the term which actually helps us to mathematically quantify what is the curvature of the manifold. Now, we have said that the curvature of the manifold can be quantized using parallel transporting a vector through a closed path in the manifold, and we will end up with a difference in the vector while parallel transporting using this terms over here, this equation. And here r alpha mu lambda sigma is equal to this format, that is partial derivative of a Christoffel symbol minus partial derivative of another Christoffel symbol with a combination of 2 different Christoffel symbols. And this term over here is called the Riemann Curvature Tensor or Riemann-Christoffel Curvature Tensor. It is commonly known as Riemann Curvature Tensor or just Curvature Tensor. And here you know that the Christoffel symbol is not a real tensor, which we have described while we discussed about Christoffel symbols. But since this comes in a combination over here, this actually eliminates the non-tensorial parts of the Christoffel symbol, and the Riemann curvature tensor here we have is an actual tensor. So now let's look into the another way of writing the curvature tensor. The Riemann curvature tensor can also be defined using the commutator relationships of the covariant derivative, which is acting on any 4 vector. Here, when it is acting on the velocity 4 vector, we can see that it is a Riemann curvature tensor into the velocity 4 vector. Again, when it is acting on one form of the momentum 4 vector, here also you can see that it produces a Riemann curvature tensor. This negative sign over here just means that I have acted it upon the one form or the covariant form of the 4 vector. Now, the Riemannian tensor actually describes the way in which one body couples with its background space, or how a body of mass forms a curvature, or how it actually deforms its background space-time. This quantity, this very notion of deformation of the space-time is given by the Riemann curvature tensor. This actually helps us studying many phenomena in general relativity, such as precession of equinoxes, etc. So actually this Riemann curvature tensor plays a very far good role in defining the general theory of gravity and general relativity. Now the Riemann tensor have many symmetries. Let's look into some of the symmetry. One of the Riemannian symmetry is that when I just interchange the these two integers over here, I get a negative curvature. This just means that when I have instead of transporting from A to B to C to D, actually I have transported it from A to D to C to B and back to A in the another path. Just by interchanging the sigma and lambda, the curvature tensor which I get will have a negative sign over here. Similarly, I have 3 another symmetries for Riemann tensor. Here I have just interchanged the alpha and mu, first 2 symbols. Here I have interchanged the alpha delta to here and these symbols to here, and I will get the same curvature tensor. And also I have another quantity such that when I keep alpha as constant and mu lambda sigma is moved in a cyclic manner, such as mu lambda sigma mu and sigma mu lambda in a cyclic nature, I will get 0. These 3 comes from the symmetries in our Christoffel symbols. You can actually prove these symmetries. You can just write the open form of the Riemann curvature tensor, just substitute for the Christoffel symbols over there, and you can actually prove these symmetries. I'm not getting into proving those symmetries in this lecture. You can do it all your own. And see, here this form over here, the symmetry 4 actually tells me that the curvature tensor is divergence free. And this very notion that the curvature tensor is divergence free holds a very important role, because In a general, when we think about anything which is happening in the space-time, we have a source, and this source we represent it as a stress energy tensor. We have learned about stress energy tensor. So we actually represent it as a stress energy tensor, any source. So this stress energy tensor, we have learned about it in our first video. This stress energy tensor turns out to be divergence free. So the very notion that the Riemannian tensor or the curvature tensor is divergence free helps us in equating these tensors to get the field equations. Actually, this Riemannian tensor, as you can see, is a 4-index tensor and it is defined in a 4-dimensional space. As per our first rule, as we have learned in our first lecture, this should have 256 components. But you can see that this Riemannian tensor has got many symmetries, and this symmetries actually boils down the number of components to n square into n square minus 1 divided by 12 components in an n-dimensional space. So let us see what happened in a one-dimensional space. In a one-dimensional space, as you can see that this term goes to 0, we have 0 component. That is, in one-dimensional space, the only possible motion is to and fro motion. And here are no such thing that I can define as a curvature, just a to and fro motion and nothing as sort. But when I parallel transport a vector to and fro, what I will get is just the same. So it's just a single line motion and nothing contributes to the curvature. So let's see, when it is n is equal to 2, what I have is a one component. And that is just a two-dimensional manifold on a three-dimensional space, just as a globe. And this one component actually is the radius of curvature. This gives me the radius of curvature. So even if it's not a sphere, say it is a distorted sphere, then also every point has got a radius of curvature. So there is one component which describes the characteristic of the curvature. Let's come to the four-dimensional space. When four-dimensional space, I get 20 components. So there are 20 components which characterizes the curvature of the manifold in a four-dimensional space. This quantity 20 is very intriguing because 20 is exactly the same number of leftover constraints which will not cancel out when we try to have a space-time to have a flat representation. When we try our normal space-time to have a flat representation, this we have 20 components which will not cancel, or we have 20 constraints of doing that. So here the Riemannian tensor also tells us there are 20 components characterizing its curvature. Now there are many variations for the Riemannian curvature tensor. One such variation is the Ricci tensor. Let's take a trace with some pair of integers in the Riemannian curvature tensor. What we will do is we will just contract it with a metric tensor, bring all its integers to the lower, and we contract it and see that this Riemannian curvature tensor can actually boil down into a 2-index tensor. So here we have already discussed we have a symmetry between alpha and nu, anti-symmetric, and also beta and mu also we have anti-symmetry that we can't just change it over. So taking trace over beta and mu or alpha and mu will only give you 0. So the only possible trace is that either you can do with beta and alpha or mu and nu. So we can just contract using these beta and alpha. So contracting using the first and 3 tensor, beta and alpha, using the metric tensor, what you will get is R mu nu. That is a 2-index tensor in a 4-dimensional space. And this 2-rank tensor is called the Ricci Curvature Tensor. And this Ricci Curvature Tensor turns out to be a symmetric tensor. It is a tensor of rank 2 and it is the only meaningful trace which we can get from the Riemannian curvature tensor. Since this has only 2 components, we can 2 rank. This has only 10 independent components which define the curvature of the space. We can again go for another variation, that is trace out the Ricci curvature tensor again using a metric tensor, and this will give you a scalar. And you know this, using the quotient rule, this will give you a scalar. And this scalar is called the Ricci scalar or the curvature scalar. So this Ricci scalar describes the curvature in 2 dimension. You know, when you have a manifold as this in a 2 dimension, the curvature at any point can be found by just drawing a circle, just drawing a sphere over there and finding the curvature of that sphere. So this Ricci scalar scalar describes the curvature in 2 dimension. And this is the simplest curvature invariant in the Riemannian manifold. The curvature scalar actually represents the amount by which the volume of a small geodesic ball in a Riemannian manifold deviates from the standard ball in a Euclidean space. So this scalar actually gives us the basic difference, the curvature difference between the Euclidean space and the Riemannian space. So let us see how can we derive the Einstein curvature tensor. We have seen that the covariant derivative commutators from which we can explain the Riemann curvature tensor. So using that covariant derivative and also our 4th symmetry, we end up in an identity called Binacci identity, and this is our identity. So when we trace over a pair of indices again, say alpha and gamma, we end up with a notation like this. We end up with an expression like this, where G mu nu is R mu nu, that is nothing but the Ricci tensor, minus half into G mu nu, that is the metric tensor, into R, that is the Ricci scalar. And this expression G mu nu is called the Einstein curvature tensor. And we can again trace over the Einstein curvature tensor and we can really get back our Ricci scalar with a negative sign. Now, towards the end of our chapter, we are going to derive the field equation for spacetime. So here we go. We have our Einstein field equation. The Einstein tensor G mu nu is equal to the Ricci tensor minus metric tensor into the Ricci scalar. And we have said that in our governing principle, all natural sources are considered to be a stress energy tensor. And we have said that the stress energy tensor is a divergence free tensor. It's a symmetric tensor and it's a 2-index tensor. We have already made our curvature tensor, the Riemannian curvature tensor, traced it and made it 2-index. So done. And after it, we have tested for symmetries and we have said that it is symmetric. And also we have said that our Ricci tensor is divergence free using our 4th symmetry. So here we have our Einstein tensor, which can be a two-index tensor, a symmetric tensor, and a divergence tensor. So this Einstein's tensor can be some scalar multiple of our source, that is our stress energy tensor. When we solve for the Newtonian gravity in an approximate limit, we solve this alpha as 8 pi g in a coordinate system where c is taken to be 1, or in a coordinate system where c is not taken to be 1, we can solve alpha as 8 pi g divided by c to the power 4. And this gives us the important Einstein equation for general relativity. That is g mu nu is equal to 8 pi g into t mu nu. Here T mu nu is the stress energy tensor, G mu nu is the Einstein tensor, and G is the gravitational constant. And this brings us to the end of the chapter Tensor Analysis. I have referred to the material of MIT OpenCourseware, and I suggest you to go for preferred readings in the given link, and I can put this link in the description box. Happy studying. Thank you.